Have you ever wondered why some apps on your phone feel lightning fast, while others feel like they're just stuck in the mud? Well, today, we're going to peek under the hood at the engine that drives that speed. It's all about something called algorithm efficiency. Let's get into it. You know the feeling, right? You're just staring at that little spinning circle, that loading bar, that wheel of death, just waiting. Now, you might blame your Wi-Fi or your phone getting old, but a lot of the time, the real problem is hidden deep inside the code. And that secret is what we call runtime efficiency. Now, this isn't just a minor annoyance. For companies, slow code can cost a fortune in server power. And for you and me, it's so frustrating that we'll often just close the app and never come back. So yeah, this stuff really matters. Okay, so to really get a grip on this, let's imagine we're going on a climb, and we're going to start on the easiest possible terrain, nice, flat ground. This is the absolute ideal, and it's called constant time. Constant time is basically the dream scenario. It means that no matter how much data you throw at a problem, whether it's a list with 10 items or 10 million, the computer takes the exact same number of steps to get the job done. A perfect example? Grabbing the very first item in a list. I mean, who cares how long the list is? The first item is always right there at the beginning. And you can see that right here in this table. The list size grows from 1 to 10, then all the way to 1,000. But look at the steps column. It doesn't budge. It's always just one single step. That is as predictable and efficient as it gets. Visually, it looks like this. A perfectly flat line. The effort just never, ever changes. It's like a nice leisurely stroll to the finish line. But, of course, most problems in the real world aren't quite this easy. So let's start our climb. We're moving on to a very manageable, pretty efficient ascent with what we call logarithmic and linear time. First up, we've got logarithmic time, and this is where things start to get really clever. Yeah, the work increases as the data grows, but it does it so slowly. Think of a binary search, like looking for a name in a phone book. You don't start at A, you open to the middle, see if you need to go forward or back, and instantly cut the problem in half. You do that again and again, and you find what you need incredibly fast. You can really see that smart strategy in the graph's shape. It starts with a little bit of a slope, but then it almost completely flattens out. Even as the data on the bottom shoots way past 1,000, the number of steps barely even gets to 10. That is incredibly efficient. All right, next up is linear time. Now, this is a much more straightforward kind of climb. The relationship is simple. The amount of work you have to do is directly tied to the amount of data you have. You double the data, you double the work. End of story. This is what happens when you have to, say, look at every single item in a list one by one to find something. And the graph for linear time? Well, it's exactly what you'd expect, a perfectly straight diagonal line. It's a steady, predictable march uphill. For every single step we take to the right with more data, we take one step up in effort. No surprises here. So really, it all comes down to brute force versus a smart strategy. The linear search just plows through everything, one item at a time. The binary search is way more strategic, cutting the workload in half with every single step. The only catch? Your list has to be sorted beforehand. But it perfectly shows how picking a smarter algorithm turns a steady hike into a nearly flat walk in the park. All right, you might want to brace yourselves. We are leaving the gentle slopes behind. We're now entering the territory of the steep, steep ascent, where things get dramatically harder. Welcome to quadratic and exponential time. With quadratic time, our workload doesn't just grow, it balloons. The number of steps is proportional to the size of the data squared. This usually happens when a program has to compare every single item in a list to every other item. Imagine a room full of people where everyone has to shake hands with everyone else. The number of handshakes grows way faster than the number of people. That's quadratic growth. And you can see it right here. That line is starting to curve upwards, and it's getting steeper and steeper. A small increase in data now leads to a huge leap in the work required. Our gentle climb is quickly turning into a cliff face. And if you thought that was bad, well, welcome to exponential time. Here, the number of steps increases at a truly explosive rate. This is what happens when an algorithm has to check every single possible combination of something, like trying to crack a password by trying 0000, 0001, 0002, and so on. The result is just stark. Look at that. This isn't a climb anymore. It's a vertical wall. Just adding one more digit to that password doesn't add a little more work, it multiplies the work by an enormous factor. This kind of growth becomes totally unmanageable, incredibly fast. So this brings us to the real climax of our journey. This huge difference in growth creates two completely different worlds of problem solving. We're talking about the world of the feasible versus the world of the infeasible. Let's put them all on one graph to see what's happening. Look down at the bottom. The flat green line, the gentle blue curve, the steady purple line, they're all just huddled together. But then look at the magenta quadratic curve taking off, and that red exponential curve shooting almost straight up. The difference isn't just big, it's a whole different universe. And computer scientists have a name for this huge divide. On one side, you have polynomial time algorithms. These are the reasonable ones. Their growth, even if it's steep, like quadratic, is ultimately manageable. On the other side, you have superpolynomial time. These are the unreasonable ones, like exponential, that grows so incredibly fast they become practically impossible to solve. Just look at these numbers to see what unreasonable really means. For a small input of 10, the numbers are big but not crazy. But jump to an input size of just 50. The quadratic algorithm takes a manageable 2,500 steps. The exponential one, it needs a number with 16 digits. And factorial, that needs a number with 65 digits. We can't even comprehend a number that big. And this is the mic drop moment. Think about this for a second. For an input of just 50 items, a factorial algorithm would take more nanoseconds to run than there have been nanoseconds since the Big Bang. That's not just slow, that is fundamentally impossible. It's infeasible. So where does this leave us? It leaves us on a quest for smarter solutions, for clever shortcuts, a quest to find feasible ways to solve the world's hardest problems. And this is the whole game. The holy grail of computer science is to take a problem that seems to require one of those unreasonable, superpolynomial amounts of time and find a clever trick, a smarter algorithm that can solve it in reasonable polynomial time. This is how you turn impossible problems into possible ones. And that's the thought I want to leave you with. So many of our biggest challenges, from developing new medicines to modeling climate change, are at their heart just massive computational problems. So what problem that seems impossible today is just one brilliant, more efficient algorithm away from being solved tomorrow? Thanks for tuning in.